Everyone is kind of worried about this. Asteroid 2024 YR4 is a 90-meter wide city killer that has caused astronomers around the world to trigger global planetary defense procedures for the first time in history. In fact, in the last few weeks alone, we've gone from no chance it'll hit us to 1% chance to 2% chance to a now kind of awkwardly specific 1 in 42% chance. Douglas Adams, is that you? Some estimates say it could unleash a devastating 8 megatons of energy upon impact. That's 500 times that of the atomic bomb that destroyed Hiroshima, Japan. But why is there so much uncertainty and confusion about where this asteroid is actually heading and whether it will actually hit us? I wanted to find out what we know about YR4 and how worried we need to be that one city is about to become the unluckiest place in the world, and ask the important question of, is it finally time to start training a bunch of oil rig drillers how to be astronauts? Let's find out. Our first attempt at spotting asteroids came in 1801, when Giuseppe Piazzi, an Italian astronomer, was charting the positions of stars across several days. He noticed that one happened to be moving. At first he thought he had spotted a comet, but its slow and steady motion suggested it was something else. After he tracked the object for about 6 weeks, from January 1st to February 11th, 1801, he boldly announced to the world that he had discovered a new planet. He was wrong. Piazzi had actually spotted the very first detected asteroid, Ceres, which, due to a combination of brief head cold and poor astronomical alignment, then promptly escaped his gaze and sailed out into the darkness of space. A similar story presents itself with YR4. On December 27, 2024, as leftover holiday cookies went stale and New Year's resolutions already showed signs of abandonment, Atlas, the Asteroid Terrestrial Impact Last Alert System, a collection of 4 telescopes across the world, 2 in Hawaii, 1 in South Africa, and a final one at El Sos Observatory in Chile, my personal favourite, were all hard at work scanning the night sky. That was until an automated warning signal rang out. An object had been spotted with a chance of impacting Earth. Within hours, what became called 2024 YR4 rose to the top of the European Space Agency's asteroid risk list, finally knocking Disturbed off of the top spot of global rock charts. This is what our telescopes saw. Early observations suggested it might just be a small 10 to 30 meter in diameter asteroid, roughly the size of a bus or small house. NASA's Center for Near-Earth Object Studies and ESA's Near-Earth Object Coordination Center collected more data to refine its orbit, and calculations suggested it would pass extremely close to the Earth but remain outside of our atmosphere. On December 31st, estimates placed YR4 now at just 20 meters across, traveling at 15 kilometers a second or 33,500 miles an hour, and it was expected to pass Earth this time within 80,000 kilometers or 50,000 miles, about 1/5 the distance to the Moon. On this first approach, it missed us, but teams around the world were already asking themselves, what would happen during its next orbits? I want to answer that question, but first I need to thank today's sponsor, MyHeritage. Because if the future has an end date, there's no better way to find comfort than digging into the past. History isn't just names and dates like YR4, your family's story is waiting to be uncovered with access to over 33 billion historical records. MyHeritage makes it incredibly easy to trace your lineage through time, through birth records, census data, or immigration documents. You might just discover a long-lost relative, or at least a better idea as to who to blame for your weird cousin Vinny. After adding a couple of relatives to my family tree, MyHeritage instantly expanded it using their discoveries tools and traced back to my great-great-great-grandpa in the early 19th century, a man by the name of Cornelius Joshua Vanderpump, hinting towards potential Dutch heritage and providing these incredible records, as well as 40 more potential matches discovered. A family of silversmiths with potentially the best name ever. If that skill set is somehow genetic, could come in handy for a post-apocalyptic barter economy. The best part, instant discoveries. With just one click, you can expand your family tree, revealing new branches of relatives, old photographs, and historical records. So if we do get vaporized by YR4, at least future historians or alien archaeologists will have a well-documented record of our time here. Take the first step into your past today. Head to myheritage.com to get 10% off and learn what incredible chain of historical events led to your existing just in time for YR4 to maybe, or maybe not, turn us all into space dust. Thank you to MyHeritage. Now back to tracking those asteroids before we become historical records ourselves. Just like Piazzi, we will only be able to collect limited data on this asteroid's trajectory. As of April 2025, it will slip from our vision, so we have between now and then to collect as much information as possible. To understand what it is that we then do with this information, we turn back to Piazzi and his lost Ceres. Ceres may have stayed lost forever, with so little measurement time possible to calculate its future pathway. That is, if it wasn't for a brilliant mathematician, who developed a new kind of maths for determining orbital pathways based on limited observation time. Later that same year, after Piazzi's initial discovery, Carl Friedrich Gauss, a 24-year-old German mathematician, developed the method of least squares, a mathematical technique used to find the best fitting curve or line to a set of data points by minimizing the sum of the squared differences between the observed and predicted values. An incredibly powerful technique and ultimately one of the many banes of high school math classes. Using his least squares method, Gauss predicted where Ceres would re-emerge in the night sky, and later that year, in December in 1801, astronomer Franz Xaver von Zach, using Gauss's calculations, successfully relocated Ceres, as the 473-kilometer-wide behemoth reappeared from behind the Sun. Now, 225 years later, we are still basically using Gauss's method of least squares to help plot the path of YR4 today. But that makes it sound simpler than it really is. One of the first problems we encounter when looking for or tracking asteroids like YR4 is albedo. Now, this isn't asteroids getting frisky in space. Albedo is a measurement of the reflectivity of a surface. An albedo of 1 is equivalent to 100% of the light being reflected. Fresh snow has a reflectivity score of around 90%, and is responsible for those embarrassing ski mask sunburns. At the opposite end of the scale, coal has an albedo rating of around 10 to 15%. The moon has an albedo rating of 7%, which I always find amazing that the bright shiny moon is actually less reflective than a lump of coal in space. YR4, by some estimates, has an albedo as low as 5%, and that's worrying. Spotting it against a pitch black night sky, despite being nearly a football field in size, is basically impossible. But albedo's influence doesn't just limit our detection capability, the reflectivity or lack thereof of YR4 is what's causing variations in size predictions. Currently, it's believed to be between either 40 or 100 meters wide, and that's not necessarily a range, it's more like one or the other. An asteroid with a darker than coal-like surface reflects a similar amount of light to a smaller rock with a shinier chalk-like surface. We think YR4 is this darker material, indicating that it may be at the 90 to 100 meter range, entering the range of city-killing asteroids. But there is a chance that it's the brighter and smaller Tunguska-like object, which ranges in size up to 50 meters. NASA is hoping to measure YR4's true size in the near future, as for about 4 hours in March 2025, the James Webb Space Telescope will use its mid-infrared instrument to determine the asteroid's physical properties, including temperature, mass, and chemical composition, which should help us understand its albedo. However, with all of those difficulties in mind, just a few days ago, estimates of YR4's likelihood of impacting Earth went up from 1% to 2% to now 2.3%, or 1 in 42 chance, meaning that all of the criteria necessary to activate the two unendorsed asteroid reaction groups, the International Asteroid Warning Network and the Space Mission Planning Advisory Group, or as I like to refer to them, the Asteroid Avengers, have now been called into action. Odds of 1 in 42 might not sound too bad upon first hearing, but the question is, would you board a plane with a 1 in 42 chance of crashing? Probably not. This means that YR4 currently ranks at a 3 on the Torino scale, which is a scale that estimates the likelihood of impact and the potential for devastation, from 0, no chance at all of impact, to 10, high likelihood of impact and global consequences for that impact. YR4 is the second highest rating ever of any asteroid we've ever detected. Only Apophis, the potential planet killer that made headlines in 2004, scored higher. But why are these estimates for impact still changing so much? There are a few other factors at play. Number one, not only like Piazzi do we have a limited observation data to work with so far, if we zoom in to YR4's full orbital pathway, the path begins to look increasingly like a straight line traveling away from Earth. At this point in its trajectory, any errors in our measurements or variation from YR4's movements that we don't accurately detect can put it on wildly different predicted pathways. This is broadly all under the banner of the chaos effect. Even with precise telescopes, our measurements of an asteroid's position and velocity have tiny uncertainties. Over time, these uncertainties compound due to gravitational interactions and mismeasurements and errors and things like that, making long-term prediction really difficult to make reliable. What we also see is that YR4's pathway isn't just as simple as an orbit around the Earth. The orbits of asteroids are affected by the gravitational pull of planets, moons, and even other asteroids. Close passes near large planets, especially ones like Jupiter, can significantly alter an asteroid's trajectory in unpredictable ways. There's also maybe a less thought of phenomenon called the Yarkovsky effect, where the heating of one side of the asteroid caused by the sun can cause off-gassing of frozen material, or can cause a steady photonic pressure on the asteroid, slowly changing the asteroid's orbit. This effect depends on the size, shape, material, and a return visit from the albedo of the asteroid, as it will determine how much pressure the sun exerts. There are obviously a few other factors, but the bottom line of this message is that this calculation is kinda hard, and it's okay to be a little off for other asteroids that don't pose much threat to us, but when they look like they will make an impact, every tiny perturbation needs to be taken into account. As time passes, each measurement will hopefully increase our accuracy of the plotting, either increasing or decreasing the likelihood of impact. That is until 2028, when it will make its next close approach to Earth, on around the 17th of December, when it will pass as close to 500,000 kilometers from us, about 1.3 times the distance of us to the Moon. The 2028 encounter will provide astronomers with the opportunity to perform additional observations and extend the observational arc by 4 years, hopefully improving calculations in preparation for our date with destiny in 2032. In the meantime though, we can run simulations. Using an orbit simulator to generate 5,000 clones of YR4 under various effects, albedos, and other characteristics, researchers have modeled future pathways and found that about 70 of them collide with Earth. This collision corridor we can see here creates a horizontal line stretching from the top of South America across the Atlantic Ocean before traversing the Indian Ocean and landing in India. Obviously it will only hit in one of these locations, and yes, it's important to remember that 70% of the planet is water and only 3% of the planet are cities, but exactly how bad in the worst case scenario could this be? If we take a city in Colombia as the impact area and assume that YR4 survives entry through our atmosphere, we can estimate with the data from a similar megaton blast using a nuclear weapon how devastating the effects might actually be. Here we'll ignore the radiation radius, which doesn't apply, but we see a 3-kilometer radius for a maximum size of fireball, which would effectively vaporize everything within that fireball. And we see a gigantic 26-kilometer radius for thermal radiation, causing third-degree burns for those unfortunate enough not to evacuate. Here for a medium-sized city, we estimate north of 2 million fatalities. But this number could be much worse. In a heavily populated area such as Mumbai, casualties could be north of 6 million. And this is all from an object that is only just slightly bigger than Big Ben. Now, beyond that dive into fear-mongering, I don't want this to be seen as pure fear-mongering. These are worst-case scenarios where the probability drops into fractions of a percent. I just wanted to find some clarity on why astronomers around the world have triggered global planetary defense procedures for the very first time. Maybe this is something we shouldn't simply forget about and hope for the best. That may at least allow us to try and figure out which movie universe we're in, either Deep Impact or Don't Look Up. But the question is, if we do choose to act, what could we actually do about it? Hollywood has made us think that detonating a nuclear device near an asteroid is pretty much the go-to method for planetary defense, but beyond the obvious geopolitical issues of launching nuclear weapons into space, how effective would this actually be? Unlike detonations on Earth, where the surrounding air transmits a shockwave, a nuclear explosion in space behaves differently. With no atmosphere to create the traditional blast wave, the primary effect comes from intense radiation and high-energy particles. If this explosion occurs close enough to the asteroid, these energetic emissions could transfer momentum and heat to the asteroid, but ultimately this would be far less efficient than the explosive forces that we are familiar with in atmospheric detonations. If, however, the bomb is placed directly on or in the asteroid's surface, the key factor driving its deflection would be thermal radiation, neutron blasts, and X-ray heating. These would rapidly vaporize surface material, altering the asteroid's trajectory through Newton's third law. This approach, often termed nuclear ablation, relies on the asteroid shedding material explosively to change course, but there is a similar method that doesn't use quite as many atomic weapons. Laser ablation involves heating and vaporizing an asteroid's surface using a very high-powered laser. The expelled material would create a jet-like effect, gradually shifting the orbit of the path, similar to the nuclear detonation. However, at present, this kind of high-powered laser is purely theoretical. What is important to understand about both nuclear or laser ablation is that they're not about pushing the asteroid. They work by forcefully ejecting material at high speeds in the opposite direction you want the asteroid to go. That's important to understand because depending on the asteroid's composition, this could result in just multiple larger fragments breaking off, which might still pose a risk to Earth, or there is a chance that over time, gravitational forces could cause the debris to slowly reaccumulate. Many asteroids, it turns out, aren't even solid rock, but are instead loosely bound rubble piles, held together more by gravity than structural integrity. This makes them very different from metallic core remnants like 16 Psyche, which are incredibly dense and tough, and brings us potentially to a third option that may be more effective and straightforward as a method. For asteroid deflection, the kinetic impactor technique is essentially crashing a spacecraft into the asteroid at high speed to change its velocity. But again, how effective is this method in the case that the asteroid isn't actually a solid rock? Well, we actually have data that tells us. NASA's DART mission, the Double Asteroid Redirection Test, launched on November 2001, set out to answer exactly this question. It targeted Dimorphos, a moonlet orbiting a larger asteroid, Didymos, and aimed to see whether a high-speed impact could significantly alter its trajectory. Before the collision, Dimorphos took 11 hours and 55 minutes to complete one orbit around Didymos. On September 26, 2022, the DART mission struck at 6.6 kilometers per second, or 14,764 miles per hour. The post-impact measurements confirmed that the moonlet's orbit had shortened by 32 minutes, a clear demonstration that a kinetic impactor can effectively shift the motion of a rubble pile asteroid. Each of these proposed solutions suffers from two significant problems. They require time and they require cooperation. The DART mission started in 2015 before successfully smashing into Dimorphos in 2022, a 7-year timeframe that required two of the world's largest space agencies to work together to plan and carry out the mission. If we start today, we might just make it. But who is going to foot the bill? A mission of this scale would require a huge chunk of already stretched budgets. In today's political climate, would NASA or ESA get the sign-off to spend billions on a mission that has a 97.7% chance of not being needed? Or are we in a more terrifying universe and we are waiting for Elon to step into the fray? Or does this make the film Don't Look Up feel more like a prophecy than a satire?
People are going to ask why we didn't act earlier, so you're going to have to take the hit on this one.
There is some question to ask as to whether nations or corporations would even get involved when they are outside of the risk-impact corridor. It could become an international game of not until 2028, and we're faced with a more accurate reality, do we make a decision? By which point, it might be too late. Currently, we are heading down the wait-and-see path, with most agencies rightfully concerned and busy collecting data in the meantime. There is, however, one notable exception. A few days ago, China just gave us a little glimpse of hope via a recruitment posting. China's State Administration of Science, Technology and Industry for National Defense is now recruiting for a planetary defense team, with the aim of diverting similar catastrophes. In a fortunate coincidence, earlier this year, China also already announced conceptual plans for kinetic impact missions aimed at targeting and colliding with an asteroid in 2030. Maybe an update to the target of which asteroid they were aiming to impact is all that is needed to save us in 2032. Regardless of China's plans, we can continue to make measurements until April, which is when YR4 disappears and won't return until 2028.
I'll be back.
But at this moment in history, the way we are responding or not responding to the threat says a lot about where we are as a species. We're in what I think of as the age of folly. We've survived successfully the age of whimsy, where all these fun things like famine, pandemic, natural disasters that lead to mass death, you can't really do that much about other than throw your hands in the air, lament and write poetry. In the age of folly, we do actually have quite a lot of the tools that may prevent these existential threats. But we also quite like short-term thinking, greed and gently persistent incompetence, which means we're just as as likely to turn these tools on ourselves as use them for our protection. Maybe one day, looking ahead to the future, we get to the age of mastery, a hypothetical place where we both understand the tools and ourselves and are capable of repelling basically any disaster that nature or the cosmos throws our way, except maybe the heat death of the universe. My view, though, is that most civilizations probably don't make it to mastery. The question is, will we? Or are we destined to become just another species that almost had the ability to control its destiny, but couldn't quite get its act together? Either way, at least we'll be collecting data for more than just an asteroid trajectory when YR4 returns in 2028. If you like this video, hit the subscribe button, so we've got some really interesting things coming up soon. If you work on a technical team and solve these sorts of problems out there in the world, I would also be interested in talking to you. I run a venture capital fund called Empirical Ventures, where I back PhD scientists and engineers to help solve some of the biggest problems in the world. I'll leave a link down in the description where you can find out more. Thanks again to MyHeritage for sponsoring this video and not only helping me discover my origins, but also bringing them to life with their research. Click the link down below to get a 14-day free trial and be amazed by what they can discover about your heritage. I will see you next week. Thanks for watching, and try not to lose sleep over any rogue asteroids. Goodbye.